All right, welcome everyone to the special focus session on general fractional calculus operators and fractional inverse problems. This will continue for the next, I believe, 8 or 9 weeks with different presentations. We're starting today with the presentation of Professor Anatoly Kochubei. Anatoly Kochubei, born in 1949, is department head at the Institute of Mathematics of the National Academy of Sciences of Ukraine. His research interests include fractional calculus, non-Archimedean analysis, partial differential equations, operator theory, and mathematical physics. We are very happy to have him opening our special session with the topic of discrete-time general fractional calculus. Please, Professor Kochubei, the floor is yours.
Thank you. As usual, I will begin with thanking the organizers for the good idea to create such a seminar, covering many topics interesting for its participants. As for this talk, its title reflects its content. It will cover 2 subjects which are different but have intersections. General fractional calculus, that is a version or versions of fractional calculus which are more general than the classical one, which contains new operators and new functions appearing as special functions of the new calculus. On the one hand, there is a discrete time fractional calculus. That is the fractional calculus working not with continuous functions, but with discrete functions, a kind of a difference calculus, but fractional. And I will try to join both these directions, and I'll just begin. First, I have to recall the main notion of both the subjects I noted. First, differential convolution operators. I will say a little later about the history of this notion. That is a good topic instead of usual differentiations, which is helpful in this theory. For the Caputo-Gerbashan derivative, this kernel K is a power kernel of this kind. So this general calculus includes this classical fractional derivative. And more complicated example is the distributed order derivative containing an integral in the order of this function. Rho is a Borel measure of 0, 1. So distributed order derivatives appeared in physics, and they are also covered by these more general objects. Our problem for general fractional calculus is to find under what conditions upon the kernel K does this operator has a right inverse, a kind of fractional integral, and produces a kind of fractional derivative equations of evolution type. The latter means in particular that this the simplest Cauchy problem, like this, with a lambda, a positive coefficient, but with minus, whether this problem has a unique solution infinitely differentiable, and completely monotone. So this equation has a solution like exponential of negative argument. And second, if we consider a partial differential equations with differential convolution operator with respect to time and the usual partial differential operator like this Laplacian in spatial variables, this Cauchy problem with good initial function must have a unique bounded solution, and we have to define appropriate notion of solution, of course. And this equation should possess a fundamental solution of the Cauchy problem, which is a kernel of the property of probability density. That is, these two properties, A and B, define a class of equation and the class of operators with respect to the time, which are the closest to classical equations of mathematical physics. The answer, which appears first in my paper of 2011, is as follows. We consider the Laplace transform of the kernel K. It should exist for all P greater than 0. This Laplace transform should belong to the Stieltjes class. In a moment, I will recall this notion, and has such asymptotic properties near the origin and near infinity. The Stieltjes class consists of functions admitting this integral representation, where A and B are positive or zeros, and sigma is a Borel measure of semi-axis, such that this integral converges. In the situation of asymptotic conditions just mentioned, A and B are zeros, and actually we consider such a kernel K whose Laplace transform is exactly a Stieltjes transform of this function lambda plus t. Under the above conditions, such functions which sends p to 1 divided by p k of p also is a Stieltjes function and admits an integral representation with a completely monotone function var kappa, such that kappa of s tends to 0 as s tends to 0. This function has also an integral representation of Laplace Stieltjes kind, and what is most important is that this pair of functions, k and kappa, form a pair of Sonin kernels. That is, if we take a convolution of these functions, our initial kernel, and this fractional integral, their convolution is equals to 1 for all t. So under our condition, this integral operator can be called the fractional integral or the general fractional calculus. And actually, fractional calculus is such a calculus where there's a fractional derivative and fractional integral, and the conditions I'm stated as a function theoretic object is sufficient for the existence of fractional integral. And it was proved that under this situation, this parabolic-like equations, fractional parabolic equation, behaves just as classical parabolic equations. If the initial function is bounded globally held continuous function, then this Cauchy problem has a unique bounded solution. And there exists a fundamental solution to the Cauchy problem that is a kernel with the property of probability density. Next, we will consider actually in this talk not quite fractional parabolic equations of classical type, but more likely this generalized subdiffusion equation of this kind, where in time variable we have a kind of fractional derivative just introduced, and spatial variables are hidden within an operator A, a closed, densely defined operator in a Banach space, which generates a bounded C0 semigroup. This interpretation of this equation in terms of general fractional calculus was done by Bazhlekova in her Doctor of Science dissertations recently defended in Sofia. Now, a couple of words in history. From this seminar, from the talk of Professor Skalas, I learned just later about this paper of 2000, year 2000. Skalas, Professor Skalas told the first part of his talk as Kochubei without Kochubei, because this paper also contains a formula for fractional differential convolution operator. It's a pity that I didn't know this paper published in a physical journal and titled in terms of finance. But anyway, this is not quite a mathematical paper. There's just a physical motivation for this kind of operators, but no mathematical theory. And there was also, still earlier, in 1985, there was a paper of Gustav Griepenberg, which also considered differential convolution operators, even nonlinear. And this is a mathematical paper, but it didn't specify those equations with properties like those in mathematical physics. Excuse me. So this paper is more mathematical. I referred to this paper in my one, but it doesn't answer the questions I formulated. Now it dealt only with well-posed equations and nothing. Next, to the second part of my subject, discrete fractional calculus. There are dozens of papers on this subject, and a monograph by Goodrich and somebody else, I don't remember the name. There are two kinds of discrete fractional calculus. That is, two kinds of difference operators with some fractional properties. One is based on nabla backward difference, and another is based on the forward difference. Actually, these papers contain forward difference too, and these papers contain backward difference. This all is interpreted in various terms, but for those who knew about this literature, I follow the approach by Lizama in the framework of nabla calculus. In the nabla calculus, we deal with functions defined on natural numbers at 0, and we can write recursively the forward difference higher order. It's just a simple work around this formula. But what is not trivial and is just an invention of the corresponding authors is the formula for fractional difference operator like this one. It's a discrete convolution with some function containing 3 gamma functions. And actually, the mathematics around this notion is contain definitions of various fractional objects based on this. And this construction is also, as a special function, has interesting properties. Below, we will use the discrete convolution notation using this so to say convolution, circled convolution, like it is written here. Now, if we have the notion of fractional difference, I just wrote return here. We can define the Riemann Liouville fractional difference operator like this one, and the Caputo fractional difference operator like this one. We have the order of deltas and nablas are different in these formulas, but these operators are connected by the relations, recalling the classical connection between Riemann Liouville and Caputo fractional operator used traditionally in fractional calculus. You see here this function rho containing 3 gamma functions. And now the next thing I want to speak about is a beautiful invention by Carlos Lizamo about connection between continuous fractional calculus and discrete fractional calculus. He considers Poisson distribution defined as usually in probability theory with these properties. And Lizamo considers the Poisson transformation of a function, of a vector function, of a bounded operator function, defined like this. One takes the functions of continuous variables and integrates it with the Poisson distribution, obtaining a sequence, a function of natural argument. In most cases, we will denote the Poisson transformation by the corresponding capital letter as it is here. U small is a function of the variable t. U capital is a function of a natural variable or zero. Then it appears that the function rho alpha 3 containing of 3 gamma functions appropriately multiplied, which is often used in discrete fractional calculus, is the Poisson transform of this function. And this function is just a kernel of classical Riemann Liouville fractional integral. This is, as for me at least, is a very beautiful picture where complicated special functions involving, for example, 3 gamma functions are obtained from the kernel which is known to everybody. Now we have convolution of function of a continuous variable, and we have convolution, discrete convolution, like was written. And it appears, as was proved by Lizamo, for under various assumptions, that the Poisson transformation transforms discrete convolution, continuous convolution into the discrete convolution of Poisson transforms under some assumptions of good convergence of the Laplace transform of these functions. And now we can try to say a little about general fractional calculus operators. First, for continuous time evolution. It was proved by Vazhlekova in her second dissertation that the Cauchy problem of this kind, where A is a generator of good semigroup, has a unique solution defining a strongly continuous bounded operator function S capital of T on the Banach space where all these objects live. Applying to both parts the Laplace transform, we obtain such an identity. Laplace transform of this solution operator is calculated via the Laplace transform of our kernel defining our fractional functions. For example, if we deal with classical alpha fractional calculus, we study the Caputo derivatives, this integral can be written this way, and it is called the alpha resolvent family. Because for alpha equals 1, this is just a usual resolvent operator A. And now we introduce the resolvent family defined in the general situation like this. Its properties are not so simple to obtain, though they to some extent similar to proofs of properties of the resolvent of unbounded operators from textbooks and functional analysis. But anyway, this resolvent family, S capital of T, is defined on the domain of our operator A and sends this domain into itself, and it commutes with the operator, and it satisfies a kind of integral equation containing the fractional integral. I recall the situation that this is not the classical fractional integral. This is a fractional integral in terms of general fractional calculus. And of course, such results are obtained usually using the Sonian identity. So some results perhaps can be proved in more general situation if we assume not Stieltjes functions, but just the Sonian identity. But so far, it is proved in the situation I described. Now, if we have protagonists of the general fractional calculus, we can introduce objects of the discrete general fractional calculus, applying the Poisson transform from continuous time to discrete time. If we have a bounded continuous vector function, u small of t, we set u capital of n, where n is 0 or natural numbers. And we can consider the Riemann Liouville type derivative, just that differential convolution operator. And there's the following identity. Though we define the Riemann Liouville derivative in the discrete case, proceeding from the one in the continuous case, we can write it independently like this thing. This is a Nabla difference operator, and K capital is the Poisson transform of K small, of our defining kernel. We have a defining kernel like this here. We have its Poisson transform, and this Riemann Liouville type operator can be written independently in terms of discrete objects. it's written here. An equivalent definition, which is a little better in the sense that here we have only n from 1. We have our functions beginning from 0. If we rewrite this formula like this is done by making a transformation of discrete variable like written here. We obtain n beginning from 0, but here the forward difference instead of backward difference. Next, we can define the discrete Caputo type fractional difference. If in the looking formula and the Riemann Liouville difference, we have some differentiation outside convolution, and in the Caputo difference, differentiation is inside the convolution, but this is a different differentiation, not nabla but delta. Or it can be written this way. And there is again a relation between the two types of our general fractional difference operator. For all n from beginning from 1, the Caputo type operator is obtained from Riemann Liouville type operator minus this function. Next, we are moving towards some applications of fractional objects to differential equations. Let us consider the Cauchy problem written here. Of course, it's not obvious that one has to choose just such kind of arguments, n on the left and n plus 1 on the right. But it's inevitable in the discrete case because in the continuous case, if we can move along our arguments from the left and from the right and get to the same point, but in the discrete case, that is impossible. And indeed, we need to consider such kinds of the Cauchy problem. We can consider this Cauchy problem with respect to a vector function, whereas before, our kernel K appearing in the definition of a fractional difference operator satisfies the conditions with Stieltjes functions. A is a generator of a bounded C0 semigroup on a Banach space. We understand the solution as a sequence belonging to the domain of our unbounded operator. Let S of T be a resolvent family corresponding to the operator A and the differential convolution operator. Let sigma be the Poisson transform of S. So, if we introduce some more notation, the Poisson transform of a fractional integral, x hat is again the Laplace transform, and we have the result that such an expression written here gives a solution of our Cauchy problem. This is more or less the first part of such activities, like fractional difference equations of the above kind. I will not go deeply into applications, but there are some applications already. For example, we can consider stability of solutions obtained here, and if A is not just a generator of a bounded C0 semigroup, but a generator of semigroup with this exponential decay, then the solution of the Kochubei problem is stable. It tends to 0 as n tends to infinity. Recently I started to consider chaotic properties of such operators. Actually, this activity was also initiated by Lizama, but of course not in this general fractional framework, but for the Caputo case. And I will not give a statement of results because we would need quite a lot of preliminary notations and all that. But I can say that under some assumptions for the function k in terms of their Stieltjes properties, the Riemann Liouville derivative of this framework defines a chaotic operator in the sense of Devaney. In turn, this has not been yet done, but in principle, that makes a possibility to consider various encryption problems of the real world. Thank you. I will be glad to answer some questions.
Thank you very much. Do we have any questions from the participants? You can raise your hand or you can simply unmute yourself. Yes, Ravshan.
May I ask a question? Well, first of all, thank you, Professor Kochubei, for very interesting talk. As far as I understand, this theory which you explain us is connected with derivatives in between 0 and 1. So that this derivative connected with diffusion equations. Is there any theory for derivatives in between 1 and 2? I mean, which is connected with wave equation?
Not yet, but it's of course possible and it's desirable that somebody does it. Because for continuous fractional calculus, there's a quite interesting theory between 1 and 2, and it must be reflected here too.
Okay, thank you.
Yuri, you are muted. If you're trying to ask a question, we cannot hear you.
Okay. Yeah. So first of all, thank you, Anatoly, for a very nice talk and for your next very important contribution to the theory of the general fractional calculus, this time discrete-time general fractional calculus. And in fact, you developed, following Lizima, of course, a kind of duality between continuous and discrete general fractional calculus operators. And in the framework of this duality, I can imagine that there are connections between corresponding results. I mean, you already considered, for example, the Cauchy problem for the general fractional derivative of Caputo type. And I can imagine that you can translate these results into the discrete world. Did you use this duality for proving, for example, this last theorem, or did you prove it independently of the continuous version?
Perhaps that's possible, but I didn't do it. Because this idea of duality, as you say, is quite beautiful and interesting, and I didn't try to avoid it.
Okay, thank you very much.
Thank you. Any further questions or comments? I can ask one thing maybe, because I heard recently about some sort of operators which are perhaps between or perhaps generalizing both discrete and continuous operators. Apparently there is a book about these so-called concretes, that's continuous and discrete. Do you think this is a useful theory to extend Sonian kernels into that setting?
Perhaps we should try. We should try.
Okay, thank you. Any other questions, comments? All right, then we thank very much again Professor Kochubei for his time and sharing this interesting theory.
Thank you all for your attention.
Thank you.
Thank you again.